How's it going, everybody? And in this video, I'm going to be talking about what makes engineering exams different from traditional exams that you would see in a class like chemistry or physics. And for me, the really exciting thing is that, and the thing I really enjoyed was that you don't really have to memorize all that much stuff. Like, there's not really huge formulas you have to memorize. And even in classes like fluid mechanics, where there are tons of formulas, you're given sheets that tell you all of these formulas. So you're basically given a toolbox and you're asked to solve a problem and figure out, so it's on you to basically know which tools to apply in which situation. It's also on you to figure out what assumptions can you make in a given situation. And so the whole point of doing these problem sets that you would get after every lecture from one of your classes as a chemical engineer, for instance, is basically figure out what are the key tools to apply to a given problem. So when you see a steady state assumption, when you see an adiabatic assumption, when you see an isochoric assumption, so just being able to pick out these words from a problem statement and know why these things would be so valuable in helping guide your decision into whether or not you would want to use one particular equation versus another. Understanding the intuition behind a lot of the dimensionless quantities, such as Reynolds number, which is arguably one of the most important values we look at in terms of, which type of laminar or turbulent regime are we in, and based on that, what other equations can we apply here to make sure that we're accurately modeling a system and going to be able to predict its behavior. And so a lot of this stuff is basically just knowing how to solve problems. And even if you don't know how to solve the entire problem and get a right answer, that's okay. It's about figuring out how much of this can you demonstrate you understand, and how much or how well can you justify the assumptions that you're making and your rationale for following a particular sequence of steps. And so in that regard, that's what I like about it. And as much as it is a grind, especially in the early years of being a chemical engineer at Berkeley, where a lot of it was just slamming your head against a wall until midnight, going down a rabbit hole, coming back up, realizing that you've made no progress on a particular problem, basically learning what not to do, is that, by the time you get to being a fourth year student as an undergrad, it is a lot of fun, in my opinion, because that's when, you still have your toolbox, and you've got a big toolbox at that point, and you can finally begin to do what I would consider art, in that you're able to really begin to create your own things. And there's more than one way of solving a problem or creating a process to create some kind of thing at an efficient rate. And so once you've understood the tools and why these tools are applicable to particular situations, you can begin to create your own processes and really think deeply about why one system is much more efficient than another system, and what can you do to further optimize the system. And so I think at the end of the day, as an engineer, like, one of the things that is most important is just efficiency, doing things as cost effectively as we can, doing things as energy efficiently as we can. And so stuff like that are the things that really drive a lot of the decisions that we make. And obviously safety is the number one priority, and all this stuff above cost or profit. We're trying to make sure that we're designing systems that are as safe as possible for people. And so I'm gonna wrap things up with that, but I do hope that you guys find this stuff interesting. I'm happy to answer any questions if you guys have any. I hope everyone out there is doing well, and I will talk to you guys next time.